Okay, so let's start our lesson today. So, yeah. So let's try about the argument about calculus. Okay. So so. Yeah, so there are limit about functions, and then and okay, maybe I think it's the computation of limits. Okay, computation. Limit L'Hopital's rules. Okay, so this is about limit of functions. So what is the sequence and series? Okay. Yeah, so sequence of series. So okay. Sequence and series. So sequence series. I think test the ratio test. Okay, so here is the theorem. Yeah, so I think it's in chapter about sequence that's saying that so but okay, I think this is the argument about real numbers, right? So namely so it says that um so it says that so theorem I think is in the real case. Okay. So real case. If we have the limit as x goes to infinity of fx is equal to L, and Fn is equal to An. Oh, okay. So when n is an integer, then we have that the limit as n goes to infinity of An is equal to L. So let's see. Let's see whether this will work or not. So so here so here we have that. So there are like okay. So here there are two things, right? So one thing is that so one thing is that so there will be a so one thing is that you have to take the limit, right? We will try to take the limit as x goes to infinity, but we cannot really take the limit of a as okay. So the question is that so what we really want. So evaluate the complex limit. Let's see. So evaluate the complex limit. So evaluate the complex limit. Let's see. So yeah. So let's see. So if f of x is equal to L. So we know that the okay, so yeah, I'm thinking of how so because I don't think there's a complex version of L'Hopital's rules currently. So I'm thinking of if there is a like high dimensional like so can we actually turn this into a one-dimensional argument? So can we turn this limit into a one-dimensional argument? Okay, so can we turn it into a one-dimensional argument? So can we turn it into a one-dimensional argument? I think we need to find some function that okay, so what do we really want? So let's see. So one-dimensional argument. so okay, so so what we need is that so find a real valued function f from R to R such that f of yeah, so I think we probably need a way to parameterize, because you want to say something like f of x is equal to the natural log of the modulus, the real log of the modulus of 1 minus, because in order to build up a function in terms of a real variable, so we need some way to, because these omega n's, they are scattered around in like a complex plane, right? So it is really like a two-dimensional object. So probably we need to somehow parameterize these omegas in terms of like one in terms of what in one parameter, within one parameter. Yes. So so can we parameterize this one? So can we parameterize so another thing is that omega I in one parameter, you want in x, like a real so I think this is not precise enough, so not parameterized, because these omega i's, they are just yeah, because these omega i's, they are just the spiraling, right? So yeah, I feel like yeah, so they are just like spiraling around the origin. So like this spiral and then going on. So so instead of parameterizing, because this x, it has to be a continuous, maybe a better differentiable function. So yeah, so maybe when I say parameterize omega I, so maybe what I should say is that parameterize a line that passing through all the omega I, right? So yeah. So parameterize a line that passing through all the omega i's, I from 1 to infinity. Yeah. So I think that has to be defined piecewise. Or okay, so but we also require, because in order to use L'Hopital's rule, we have to let this line to be differentiable, right? That allows us to take the derivative. Right? So so because if I want to, yeah, so maybe I think the first step is to determine what the line is, because if there is a, if the line has the corner point like that, like at this point the line is not differentiable, so probably I won't be allowed to take the derivative at some point, right? So I need to avoid that. So how can I avoid that? Yeah, so how can I avoid that? So let's see. So okay. So can we actually so can we actually, yeah, but if we run out of the circle, then it might be very hard to compute the derivative, right? Yeah, it might be hard to compute the derivative. So let's see what happens. So so what is a line that easy for us to compute the derivative, but still, yeah, and also passing through all these points? Or it has to be a, or even if we do so, but